Sean.
Hello, good to see you.
Nice to meet you here.
Good to see you.
Yeah. Right. So everybody's okay here? Everybody here for the speakers?
Yeah.
Oh, that's great.
And
that's great.
yeah, Tao also said he would be here. So before starting this section.
Yeah, he's chairing the session. Number
one
session.
So
yeah, that's why he's
maybe he's also chairing other session.
Yes, you're right. You're right. Session A. Session A. He's now chairing. Yeah.
Yeah, he said he would speak several words to our session, but maybe now we can start now. So
all right. So now it's time to start. Yep.
Yeah.
See you.
Okay.
See you.
Bye.
Okay. So our session is membrane distillation, and it's pleasure to chair this session with Dr. Alex. I'm Ying Chaodong from Dalian University Technology. So our first speaker is Dr. Alex Volkov from the AV Top-View Institute of Petrochemical Synthesis from the Russia. And Dr. Alex title is the speaker presentation title is thermally-driven process assisted with membrane condenser. So let's welcome Dr. Alex. Yeah.
Yeah, thank you. Sorry, I'm going to make the share screen. Okay. Can you see my presentation?
Yeah, it's good.
Okay. Okay, thank you very much, and good afternoon, good morning to everyone. And today I will talk about the application of membrane condenser for the thermal-driven processes. And I will talk about two applications when we use porous and non-porous membranes for that application. While when we consider air gap membrane distillation, so there was a concept that is presented here, and in that case we have air gap in which the water is evaporated through the porous membrane and then condensated on the cooling plate, and which is non-porous. And that application has certain limitations that we have to orient our module in a vertical way. And secondly, that we cannot reduce the air gap thickness because the condensed water drops would contact the backside of the membrane. However, air gap offering additional heat isolation, so that means that we have lower heat loss in contrast to the direct contact membrane distillation. And what we are proposing is that to use the porous condenser system when we replace non-porous plate with a porous membrane. In that case, the water is condensed on the cooling porous membrane and then immediately sucked by the coolant, because we keep the pressure, liquid pressure here, a bit lower than the pressure in air gap. So that means that we do not have the water drop on the surface, and it allows us to reduce the thickness of the air gap. What we've done, so to prove that concept, we've made different orientations, let's say, and we put a membrane in a classical way with the vertical orientation, but at the same time we've tried a different horizontal one when the membrane is on the top side or below the air gap. We've done that for the air gap membrane distillation and also thermal preparation for the recovery of the organics from the in that case butanol from its aqueous solution. And the thing that we didn't find any deviation in a flux, noticeable one, in a contrast with the different orientations. So there was the same water flux and same separation factors for the both applications. So that confirms that in the using of membrane condenser, it's sufficiently enough to evacuate the liquid from the air gap. Well, when we start to think how to use that application, so it's we have a joint projects between Professor Tauhe and my lab, and that's focusing on the lithium recovery. And for the Professor Tauhe part of the project, so he's focusing on the extraction of lithium from the brine solution. And in that case, we have to increase the lithium concentration in the water from 2 grams per liter or even more. And when we consider different geothermal waters in Russia, so there are a different one, and there are only two examples with the lithium concentration 0.14 and 0.48. So that means that we have to concentrate our stream by a factor of 10 or 20. But if we take into account other salts, so that means that we have to deal with the high concentrated streams and even some at saturated conditions. However, when we had a look on the literature, there are many publications that are dealing with the membrane distillation. However, there are only a few papers that describes the application of the membrane distillation with the high saline solutions and saturated solutions. And there are only just few papers, as you can see here. And the thing that when we had a look on the performance of the membrane and the regime of the application, so we can see the duration of one single run before the flashing, that's usually just few hours. At the same time, there are dramatic drop in the water flux within one single run. And when people wash the membrane, so there was a certain recovery ratio, and the number of the cycles was like a 6 to 3. So that means that people didn't focus on a long-term operation, and we can understand that it's quite difficult to run that experiment because there is also crystallization of salts, and extra cares have to be taken into account to provide the successful operation of the membrane distillation unit. Bearing this in mind, so we've decided to simulate that process by using a Simulink. That is a software that allows to link with each other different units in order to understand how the performance of each stage might influence their performance other stages. And as I said before, there is 2 units. The membrane distillation module that just concentrate the feed stream that goes to this solution tank of the system. Extra water is evaporated, so that means that we have also crystallizer that remove the corresponding amount of the salt. And then the brine solution goes to the membrane extraction unit. In this simulation, so there is a question for the mass of flow, and that is on the membrane distillation, and that is a function that describes the change of the water flux of evaporated through the brine. That's function of the feed temperature, active surface area, number of the modules there. It would take like a 2.5 meter, and zeta, that is a parameter that describes the iteration of the membrane performance due to scaling or fouling. And for the Z, so we use our data on the membrane distillation with the membrane condenser. So there is a first run that is just a blue dots. Then we did washing, and we've ran the second run, and there was nearly the same position of the points. So that means that we've got almost totally a full recovery of the membrane performance. So we used that equation to describe the flux drop over the time. And that's like a typical example of the system performance. Let me explain here. So that the blue line, that is evaporation of water. So that means that we have the drop of the flux due to fouling or scaling. Then we have a washing. So there can also mark like a red line here. So that means that after the washing, we have recovery of the flux. And in that simulation, we've in that particular example, so the runtime before the membrane washing was 4 hours, and the recovery rate was 99%. So that means that after the washing, we have a 99% of the initial flux. And once the membrane falls to the 50% of initial performance, like here, so we have replacement of the modules. So that means that that is part of the graph just represent the replacement of the module because of inability to restore the water flux up higher than 50% from initial flux. A black line, that is a lithium recovery, and the orange one, that is amount of sodium chloride recovered in membrane crystallizer. Well, what we've done, I'm sorry, that's, can I just remove that? Okay. Okay, anyway, on the X, so we have just right runtime. Runtime means that the time that we run the membrane module before the washing. On the other X, that is recovery ratio. So that is a ratio that is a flux after the washing that we recovered. And I think that the membrane performance and the fouling plays a major role, and the runtime before the washing is important, but the most critical value, that is recovery ratio, because if we have quite low recovery ratio, 95%, let's say here, so we can recover only like up from 100 up to 200 grams of lithium per module used. That means that we recovered the lithium, but then we have to throw away the membrane module, and bearing in mind the cost of the lithium in the market. So that means that we need to get quite cheap membranes, quite effective one that could run for a long time, but the most importantly, it should be stable towards fouling, irreversible fouling, and scaling. So that data just indicate that if we consider long-term operation, the performance of the membrane plays a critical role, especially towards fouling and scaling. So also when we just did ran, so we've also found the precipitation of salts on the membrane, on the membranes, but most importantly that if you have a quite complex composition, so we've also added kerosene and also surfactants. So that in that case, we found the increase of conductivity of the cooling path. So that means that we have a leakage through the membrane. Bearing this in mind, so we've proposed to get rid of the membrane from the hot part, but to use only the membrane condenser in a cooling part. So that's a kind of the combination of air gap membrane distillation and also film distillation. But in the case of the film distillation, so we have condensation outside of the unit, which means that that's quite long pathway of the water molecules to be condensed. And in our proposal, so we've combined both approaches. So we use thin film distillation with the placing of the membrane condenser system inside of the system. So that means that we do not have the contact of the membrane with the thin film liquid feed. So that means that we do not have the problem with the fouling and the wetting of the membrane, but at the same time, application of the membrane condenser inside of the module allows to reduce the air gap thickness here, and also to short the pathway of the molecules from the hot surface to the cooling parts and the liquid circuit. So we've done a different experiments here with the concentration of the sodium chloride from 50 gram per liter up to saturation conditions. And with the playing of the temperature, like 60-20, that is a green line, and 80-10, that is a blue line. So that was possible to get the saturated solution quite effectively within short time. But the most important in that, since we do not have a contact of the feed solution with the membrane, so addition of the hydrocarbons like kerosene or surfactants did not influence the performance of the system. So that means that with that kind of the concept, we can use that system for the quite severe conditions like saturated solutions that can combine different compounds. I will just go shortly through that part. So this process quite easy to simulate, and with regards of the temperature, so we can achieve the flux up to 20-25 kilo per square meter per hour. That is air gap like 2 millimeters. And the thermal efficiency would be at the pressure at the temperature difference when 40-50, but a more effective process would run at a high temperature. And we've also tried different galvanic waters. So that's also possible to concentrate copper, nickel, and iron content streams as well. And the same concept was used for the non-porous membranes. So that is for the recovery of the organics from the fermentation broth, which might be interesting for the bioeconomy and the booming activity on the development of the biomonomers for the chemical sector. I think that when we use the membranes, there is a fouling problem, except the stripping conditions. But in that case, we can recover only volatile organics, but at the same time, non-volatile organics are accumulated within the fermentation broth, which might inhibit the further activity of the microorganisms. So that means that we cannot always use the membrane stripping. But the problem of the system when the membrane contact the fermentation broth, that is a fouling by those compounds that cannot be evaporated through the membrane. And in the application with the porous condenser, so we use the ability of the porous condenser to pass the liquid through the air gap and then evacuating that liquid. So that means that we have a common run when the hot feed solution contact the non-porous membrane. That's like 4 hours, let's say. Then we just remove the feed from the feed compartment, and we fill the air gap with the organic rich phase, let's say. In that case, organic rich phase just extract all of that compounds that are absorbed by the membrane, but importantly that we do not feed the organic liquid into the feed compartment, so we just have a separation of the both liquids by the membrane. So that means that we do not need to flush or wash the feed compartment before the entering of the fermentation broth. Then extraction process takes place, and then we just turn on the coolant pump, and the organic rich phase go through the porous condenser back to the coolant circuit, and then we can just run experiments once more. Well, in that application, so people usually use thin film composite membrane, but for that kind of that application, so we've proposed to use the dense membranes, because that process is not only on the permeation of the organics through the membrane, but the membrane also acts as an adsorber. So it's also absorb organic compounds. So that means that we have to provide sufficient absorption capacity before regeneration. And that's just a schematic overview of our module. And that is results just indicate the run of the one membrane within long term of the operation when we did in situ regeneration. But once we stop do that, we can see that the flux went down. So that means that through that time, our system was effectively towards the non-volatile compounds that was presented within the fermentation broth. When we did analysis, so we found that when we did in situ cleaning, the cake layer was 3 times thinner, so there was like 5 microns, in contrast with the performance when we didn't do the cleaning, and the cake layer was 15 microns. When we did analysis, so we found that deposit on the feed side of membrane surface is less pronounced rather than backside backside of the membrane, because backside of the membrane was clean, so there was no internal fouling. So that means that we can effectively extract those compounds from the airmate side of the membrane. And when we did also analysis of the extraction liquid of the soaking of the membrane, we found different compounds that indicate internal fouling. So that means that the membrane can extract those compounds, and then we can remove it with the organic phase. Well, just sum up of my talk. So in that application, when we use the membrane condenser system, so it allows to reduce the thickness of the air gap from few millimeters up to 0.1 millimeter, what we did. And secondly, that application with the fermentation broth, we can effectively generate the membrane, since the porous condenser system allows to pass the liquid and deliver the liquid directly to the permeate side of the membrane to maintain the extraction of the different compounds that cannot be evaporated to secure long-term operation of the membranes. And thank you very much.
So thank you, Alex, for a very wonderful presentation. And we have maybe 1 or 2 questions. So is somebody to feel free to talk with Dr. Alex. Maybe you can also leave your message on our Q and question, the function, using the Q question and question this function. You can leave your question and comments to Dr. Alex's presentation. So I have a question. So very interesting talk and about the FCMC process. So you just combined process with different functions. So did you consider the energy consumption of this process? So during the whole operation?
Well, we are just currently calculating those things because as I said before, that we have a different energy efficiency with regards with the temperature of the hot solution and the cooling solution, and the surface energy. So that's mostly relied on the evaporation of water. And that's kind of that system that's resistant towards the fouling and scaling. In that case, it might be interesting for the treatment of the hot solution like geothermal waters. So which is quite challenging for the system when the membrane is contacted the feed solution. So that's answering your question. That's really related to the origin of the feed and whether you have a waste heat or not, because still heating of the water, that is a key part, while pumping and a circulation that is less cost less energy than the heating.
Okay, the simulation result.
Mm-hmm.
Okay, yeah, using the mathematics model. And okay, thank you. So thank you, Dr. Alex. Thank you very much. So our next speaker is Professor Tang. Professor Tang from the Department of Chemical Engineering and Material Science, Tianjin University of Science Technology. So Professor Tang holds many big projects, several big projects, and have already made some achievements in the fields of the membranes, materials, and the membrane process for different applications, using different membrane separation techniques, such as the membrane distillation and pressure-driven process. Dr. Tang's presentation title is Superhydrophobic Modification of polypropylene membrane based on ALD process. So welcome, Dr. Professor Tang. So welcome to start your presentation.
Thank you, Chairman. Good afternoon, everyone. I'm Na Tang from Tianjin University of Science and Technology. The title of my topic is stable construction of superhydrophobic surface on PP membrane with atomic layer deposition for high salt solution desalination. Water resources pollution and freshwater scarcity have become serious and urgent issues to be addressed. The effective treatment of seawater, brackish water, and high salinity wastewater is of great importance for the sufficient and safe supply of water resources. Membrane distillation has been proposed as a promising technology to treat the saline water. Membrane distillation can treat high salt solution with simple equipment, and it has low energy consumption and easy to use cheap heat sources such as solar energy, waste heat from power plant. Especially the rejection of membrane distillation is always higher than 99%. The desalted water can be drank directly. The requirement of membrane used in membrane distillation are high porosity, high mechanical strength, good temperature resistance, chemical stability, and higher hydrophobicity. The hydrophobic property of the membrane is crucial for membrane distillation. It determines the surface life and the separation performance of membrane by influencing their anti-pollution and anti-wettability properties. Therefore, superhydrophobicity modification on consumer membrane can effectively improve the continuous operation time, and it maybe can applied in high salt solution treatment. In other reports, the superhydrophobic surface usually fabricated by creating regional structures on modifying low surface energy materials or combining both. Herein, I use a new method to modify membrane surface, ALD technique. Titanium precursor can be deposited layer by layer on the membrane surface under vacuum and convert into titanium oxide under water steam. It offering precise thickness, controllability, and having excellent conformity and uniformity. In our experiment, TTIP was firstly absorbed on absorbed onto the PP membrane surface, and the unabsorbed TTIP was cleared by nitrogen. Then water was pumped into a chamber, and absorbed TTIP react with water, produce hydroxide groups, which served as active sites with TTIP in the following cycles. Accordingly, only one layer of TiO2 was deposited during one cycle. After hundreds of cycles, the PP TiO2 composite membranes was get. We call it a titanium membrane for short. It is only an intermediate product. Titanium was a transition layer on the membrane surface, and it constructs an active layer for later modification. These are SEM images of PP and the titanium membrane with different ALD cycles. We can see that they are almost the same in the picture. This indicates that the ALD process is mild enough to keep the original microstructure of PP membrane. We evaluated the performance of the membrane modified only by titanium oxide, and the results there were here. After 100 ALD cycles, the contact angle of the membrane surface decreased significantly. It shows that titanium oxide has been deposited on the membrane surface, although it cannot be seen in SEM photos. As the number of cycles increases, the contact angle decreased gradually, but they all have similar porosity and pore diameter compared with PP membranes. At left, it is XRD of the PP membrane and the titanium membrane. Compared with the two spectra, the peak of titanium do not appear, neither rutile nor anatis. This is because the titanium formed at low temperature is in amorphous form, but the diffraction peak of PP phase are weakened. This further confirms the membrane surface is partially covered by titanium. For the right figure, titanium element was detected by SPS. Then we prepared the PP-TiO2 NMES composite membrane. This is our ultimate membrane. We call it a silica membrane for short. Firstly, UV illumination on titanium membrane to produce hydroxyl radical. Then titanium membrane was immersed in NMES ethanol solution. Then low surface energy nanosilicon emulsion was reacted with titanium on membrane surface. The ethoxyl groups of NMES was to begin with substituted by the hydroxyl groups through hydroxylase reaction. The generated hydroxyl groups react with the hydroxyl groups on the silica surface by TiO(Si) bond. After that, the superhydrophobic silica membrane was obtained. The silica membrane was multi-level structure. The top layer is silica. It is superhydrophobic, and the intermediate layer is titanium, which is mainly used to bond the membrane and the silicon. And the bottom is PP-based membrane. The left figure is about water contact angle. We can see that contact angle increases with NMES concentration. At 1.2%, the contact angle is up to 159 degree, 58 degree, which is meet to the requirement of superhydrophobic membrane. The right figure is about water slip angle. A water droplet on the silica membrane is easily to roll off at a 2-degree angle. This indicates that the silica membrane has low adhesion and hydrophobicity. In these two figures, we can see silica membrane has similar porosity and pore diameter compared with PP and the titanium membranes. This is because the surface modified layer is very thin. It doesn't have a great impact on the separation performance of the membrane. In FTIR spectrum, the wide and strong peak at 1,100 in silica membrane is asymmetric stretching vibration of the SiO(Si) bonds, and the two strong peaks correlate to CSI stretching vibration appeared at 1,240, and a weak peak, 960, was related to TiO(Si) group. This is indicated the existing forms of titanium and silica. Moreover, the peak of carbon chain decreases on the surface of titanium membrane and the silica membrane. It shows that the PP on the membrane surface is less and less. The EDS mapping was taken to confirm that the membrane is of precisely persistent modification. Carbon is distributed in the whole membrane cross-section. The distribution position of oxygen and titanium are similar, both of which are distributed in the upper part of the membrane. For the silica, it only appears on the membrane surface, extremely thin. In the left SEM images, we can see that the ALD process don't change a membrane structure, but surface and cross-section. But NUMS reduced the pore size of the membrane surface. It also has no effect on the section structure. AFM topography measurements suggested that the surface modification changed the surface roughness of the membrane. Silica membrane has a minimum roughness. In this research, the roughness has nothing to do with the increases of membrane hydrophobicity. It indirectly shows that the low surface energy material on the membrane surface is the key to improve the hydrophobicity. In left figure, the tensile strength and the elongation at break of string member were almost the same. In the right figure, the T-type peeling strength test was employed to assess the binding strength between the modified layers and the membrane. The silica membrane has the strongest anti-peeling strength, whether removing the titanium layer or avoiding the titanium illumination. Anti-peeling stress reduced significantly. 15% sodium chloride solution was used for VMD test to compare the performance of the PP and the silica membrane. The rejection rate of silica membrane remained above 99% for up to 25 hours. The contact angle of the pristine membrane decreased to 103 degrees, while the silica membrane still has a superhydrophobic property. After VMD test, a certain amount of sodium chloride crystal falling could be observed on the pristine PP membrane and in membrane pore, while crystal deposition happened on the silica membrane. Let me sum up this work. We prepared a composite membrane by ALD and photo deposition. It has a titanium transition layer and a silicon superhydrophobic layer. The contact angle of the composite membrane is up to 158 degrees, sliding angle below 2 degrees. The superhydrophobic membranes exhibit an excellent anti-wetting capacity in vacuum membrane distillation. Thank you.
Okay, thank you, Professor Tang. Very nice talk. So any question?
So I have a question that thank you very much, and yeah, thank you. I can comment about the long-term stability of such coating. Have you tried to perform that membrane together with the cleaning or with the long-term of membrane distillation?
Cleaning?
I mean, have you tried to clean your membrane afterwards? I mean, it's take into account long-term operations, so you might probably need to clean the membrane. How that coating is stable towards cleaning agents or backwashing?
Washing membrane. You mean cleaning the membrane?
Yeah.
The membrane generation. So yeah.
Yeah. For the general desalination for the sodium chloride aqueous solution process, we just use water to cleaning the membrane and finish the one cycle. And then we found the different time to another period, we can begin a new period.
Just clean water.
Yeah.
Okay. Yeah, thank you.
Okay.
Thank you.
Okay, thank you, Professor Tang and Dr. Alex. So you will be your chair next following too. Okay.
Okay. Thank you.
Okay. Yeah.
Okay. Thank you.
Thank you very much. And the next speaker will be Dmitry Edhov from Moscow State University, and he will talk about the application of graphene oxide membranes in evaporation and membrane distillation. Dmitry, of floor is yours. Please go ahead.
Mr. Chairman, thank you for your introduction. I would like to introduce my research topic devoted to inoperant study of water and alcohol transport through the graphene oxide membrane in water evaporation and membrane desalination. Okay, why are researchers interested in graphene oxide utilization in such processes? The pioneering work published by Nair in 2012 demonstrates that water can pass through the graphene oxide membrane quite fast, whereas other both polar, such as ethanol, or non-polar, such as hexane, liquids doesn't pass through the membrane. And so researchers tried to utilize these membranes both in water, in air dehumidification, and in preparation separation. As you can see on the slide, I show the like a Robson like diagram for preparation performance of graphene oxide membrane in water alcohol separation processes. As you can see, graphene oxide membranes demonstrate the characteristics higher in comparison with polymeric membrane, and the characteristics of graphene membrane is quite similar to zeolite membranes, but they can prepared on the asymmetric substrate, on the porous substrate quite easy. So what is the mechanisms of water transport through the graphene oxide membrane? The main mechanism is diffusion through the interlayer galleries. Also in the layer of graphene oxide, there are some defects, and the transport through the defects also can occur. And the last non-selective flow mechanism is a parasitic flow through the stacking defects. So what is the key factors which determine the performance of graphene oxide membrane? First of all, membrane thickness, then average size of nanosheet, because the average size influence on the labyrinth pathway length. Of course, interlayer distance will have a significant influence on the both separation and permeation rate. And I can say that graphene oxide is very diverse chemical in its chemistry, and it can be prepared by different routes, for example, Hammers or Brody technique. That's why different carbon to oxygen ratio that's why carbon to oxygen ratio can vary in graphene oxide. So how I would like to present our report, our research. First of all, I will discuss the influence of average graphene oxide nanosheets influence on the membrane permeance, then discuss chemical composition influence on the membrane permeance, and on the last stage I will discuss, I will show you the results of inoperant study of interlayer variation during water permeation through the graphene oxide membranes. We can prepare graphene oxide nanosheet using Hammers technique with different precursors. For example, thermo-expanded graphite or even single wall carbon nanotubes. And this allow us to vary average sheet size from 3 microns to even nanoribbons with a length about 100 nanometer. We use spin coating technique for preparation membranes on the porous supports. Anodic alumina was utilized as a porous support, and spin coating technique allow us to form the selective layer with thickness about 50 nanometers, and the nanosheets is quite uniform distributed on the membrane surface, which was proved by both scanning electron microscopy and mapping of G-mode and D-mode intensity of graphene oxide. As you can see on the millimeter scale, we have a uniform distribution of graphene oxide nanosheets. So we try to study the water vapor transport, and as you can see, the average size of graphene oxide nanosheet have a significant influence on the water vapor permeation, because membrane formed from graphene oxide prepared from thermo-expanded graphite, so-called TEGO, have significantly lower selectivity with in comparison with membrane formed from medium flake graphene oxide and even carbon nanotubes. However, what we face with one problem with nanoribbons, because because nanoribbons have low aspect ratio of thickness to lateral size. That's why nanoribbons formed not ordered structure, and this structure contains a lot of defects. That's why the selectivity from water to nitrogen is quite low. Whereas when we turn to nanosheets with lateral size about 800 nanometers, we significantly increase the separation factor between water and nitrogen. So thus we can conclude that the optimal microstructure can formed from nanosheets, but the size of nanosheets should be less than 1 micron. Okay, let's turn to the influence of chemical composition on membrane permeance. As you can see, the carbon to oxygen ratio in graphene oxide can vary from 1.7 to about 3. So we are interested in a study of dependence of both permeance on composition, and the graphene oxide with different composition was obtained by very graphite to oxidizer ratio on the first step of Hammer synthesis. And we obtain different graphene oxide suspensions with C to O ratios from 2 to 1.7. As you can see, these structures demonstrate quite similar sorption capacity, and the variation of interlayer distance with humidity is similar, whereas we observe quite different permeance for obtained membranes. And when we increase the C to O ratio, we observe the decreasing of permeance due to lower diffusion coefficients of water in non-oxidized structure, because increasing of C/O ratio leads to decrease of graphene oxide hydrophobicity. That's why the water vapor permeation decreasing. So we know the optimal oxidizing, the optimal C to O ratio. We know optimal lateral size of nanosheets, and we turn to in situ and in apparent technique of study graphene oxide. We use such kind experimental cell with cabinet with two transparent for X-ray beam Kapton windows, and on the top side of membrane we control humidity, and from the bottom side, from the permanent side, membrane was blown by helium, and detecting of water presence in helium allow us to measure membrane permeability. Thus, we can simultaneously know membrane permeance and despacing. What we obtain, first of all, with increasing relative humidity, we observe the increase of interlayer space of graphene oxide, and we can observe so-called layer-by-layer filling of interlayer space with water molecules. If we have quite low despacing, less than 9 angstroms, the permeance of membrane is quite lower. Then increasing of humidity leads to increase of membrane permeance, and if the despacing is higher, average despacing is higher than 2.5 angstroms, we observed so-called we can fit the obtain membrane permeance using simple Puazelli flow equation, taking into account the effects of capillary pressure. To prove these results, we perform a molecular dynamic simulation, and we observe the layer-by-layer filling of interlayer distance. If we have a 1 layer or 2 layer of water molecules in graphene oxide, these layers are quite strong bonded with both oxygen containing groups of graphene oxide. Whereas if we add 1 more layer, middle layer between 2 layers bonded with graphene oxide, these layers screen the electrostatic interaction, and the middle layer can move quite fast through the interlayer space. That's why we observe like a Puazelli flow. And also we perform some experiments with study of despacing in alcohol atmosphere. We observe the similar behavior like in water, whereas the despacing for alcohols, which is bigger molecules, we observe a bigger despacing. Also, the permeance, the dependence of permeance with relative vapor pressure for alcohols is quite similar, whereas the absolute values in comparison with water is 300 is three order of magnitude lower. That's why we need to also we want also to make a molecular dynamic simulation to estimate the nature of diffusion selectivity for such kind of membranes, because surfing capacity for alcohols in graphene oxide also quite high. That's why the main we consider that the main point of selectivity of graphene oxide membrane is in preparation process is diffusion selectivity. So I can conclude that the microstructure and chemical composition of graphene oxide have a significant influence on the water vapor transport. Also, the absorbance of molecule in interlayer distance have a crucial role on the graphene oxide transport characteristics. And in large despacing, we can observe like continuous medium flow. Okay, thank you for your attention.
Thank you very much. And there is a question from the chat. Can you just have a look on that?
Yeah. The question about the stability during membrane desalination process. Yes.
When the feed temperature like ATC.
Yeah. It's quite interesting question because typically preparation performed under if we simply place graphene oxide membrane into solution, of course we can observe the delamination of graphene oxide due to swelling processes. Whereas typically preparation processes provide under vacuum and under vacuum on permeate side and atmospheric pressure on the feed side. So we have a pressure gradient, and these pressure gradients stabilize membrane during preparation process.
And the presence of organics in a feed solution, can they also trigger the elimination of graphene oxide nanosheets?
It depends on type of organic. Typically for water alcohol,
I mean, let's see. If we talk about the real system, there it might have complexity of the presence of the different compounds.
Unfortunately, I cannot answer on this question because typically we study we perform our experiments with model solutions like water with ethanol. But it will be interesting to perform experiments with real system to have complex organic compounds.
Okay, thank you very much. And with this, we're going to the last presentation, and the last presentation will be given by Yang Changdong from Dalian University of Technology, China. And the talk will be about the application of inorganic desalination membranes with enhanced performance. Please go ahead.
Oh, thank you, Alex. And it's a pleasure for me to introduce our recent work in the last 2 years about the membrane distillation. So I'm Ying Chaodong from Dalian University Technology. So first, I would like to introduce our university. And so in China mainland, on university, sometimes ranked the top 20. And our school is focused School of Science, Environmental Science and Technology. We ranked 6th in the discipline of environmental science engineering, and also we ranked A- in 2016. So first, we can talk the water treatment using membrane technology. So we can get not only the pure water, but resources and energy from wastewater, and compare the traditional separation technologies, especially distillation. So membrane technology has some key sustainable natures, like very low or relatively low energy and chemical consumption and small footprint. And membrane separation is an emerging technology, not only in chemical engineering, but environmental engineering. We can separate different species with different size using different membrane process. So especially for seawater and also industry saline or hypersaline wastewater, we can use membrane to treat. So compared to the polymer membrane, ceramic membrane can be already used in different industry like food, chemical, biotechnology, and pharmaceutical. And especially ceramic organic membrane has very unique technical advantage, like very highly stable in structure and in some under very highly very stable in under very hard, especially very chemical harsh conditions. So already increased interest in the in organic membrane. So for organic membrane market, ceramics membrane dominate the whole market, and also there are more the increasing instrument of the ceramics membrane plant all over the world. So not only in China, but also in Singapore and US and Japan and Europe. So it's already the Singapore already they are already started to install the world biggest ceramics membrane bioreactor. So and they will finish maybe in the 2 years. But if we use ceramics membrane for water treatment, especially for waste treatment and also precise separation, so there are some key issues, especially in membrane cost. So the material cost and the processing cost. But we can compare the other membrane types. So ceramics membranes have a very long, much longer lifespan cost. So much longer lifespan. So its life service cost is much cheaper than other membrane. Also, it's very challenging to improve the membrane's performance, especially in selectivity and for some more advanced precise separation. So in the past years, we first devote our efforts to develop low-cost ceramics membrane by studying the membrane materials and to study the membrane structure and then properties. We developed a novel viscous structure of ceramics membrane, and also we understood the mechanical strengthening mechanism. So we also not only did the lab scale fabrication, and we also set up with a pilot scale production to produce different membrane with different dimensions. So from small dimension to large dimensions. And also we cooperate with enterprise to develop the membrane equipment. So for application of olive wastewater treatment in industry. And it's very challenging. It's very challenging for ceramics membrane for precise separation. So it's for example, the distillation, especially at a very chemical extreme environment. So our recent years work focused to develop a novel selective layer on ceramics membrane to achieve this function. So first I would like to talk the pressure driven membrane process. So since especially for nanofiltration, it's hard to separate sodium ion. But we developed the ceramics-based graphene oxide layer to achieve this function. The key issue of the geo membrane layer is insufficient selectivity, and also is very poor stability in water. So we proposed a novel cross-linking strategy using MPD and TO molecule to develop ceramics-based geo nanofiltration membrane to improve the rejection of the monovalent ion, the sodium ion. So we can get the rejection of the sodium ion above the 19%. And also we tried use this membrane for separation different inorganic salts and micropollutants. We achieved a co-enhanced permeability and selectivity. And we also understood the cross-linking mechanism and the sieving mechanism for different species. So for the separation of inorganic salts and the micropollutants, there are size sieving and electrostatic interaction and donor exclusion, and especially we observe the partial dehydration. So this mechanism. And for saline with water, our work focus on the forward osmosis, since it has low energy consumption at ambient pressure, very low pressure and low volume. But the current FO membrane usually suffer from insufficient stability and hydrophobic and also not high mechanical strength. We just developed the defect-free high-quality PA layer on ceramic substrate, but it's very hard, experimentally hard to form a high-quality PA layer on ceramic membrane. Our idea just to introduce a nanocomposite interlayer, the titanium and carbon nanotube, to improve the quality of the PA layer. We can get a much thinner the PA under the PA layer with and without the membrane process. But if for hypersaline with water, so because the current membrane like RO is very challenging for RO, because the hypersaline with water has a very high osmotic pressure. So we used the thermal membrane hybrid process like MD and the PV process to treat such kind of waters. So for MD process, the key step is to develop the hydrophobic or super hydrophobic porous membrane. But the current organic membrane suffer from very not insufficient the stability, especially during long-term operation. And the ceramics membrane has a very excellent stability in at high temperature and at high saline water environments. But the current ceramics membrane is inherently hydrophilic. We have to modify hydrophilic ceramics membrane to hydrophobic. So, but the usual way is using the FS grafting, but FS grafting also suffer from very not good the thermal stability during operation. So because they're just a very weak bonding force. So our idea to develop the hydrophobic nanotube, carbon nanotube hydro network. So in situ grown on ceramics, porous ceramic substrate. And we obtain very highly hydrophobic surface, and especially during long-term storm, the hydrophobic super hydrophobic is very stable. So it's much stable, and also such membrane have very high flux and high rejection, better than existing inorganic membrane. Since carbon nanotube is electric conductive, so we applied the electrochemical assisted the DCMD process, so to achieve anti-fouling performance, because we just using the membrane as the anode, using the cathode, and the titanium metal use the anode. So by the electrostatic repulsion, so the anti-fouling function achieved. And also we use the electricity, but we can produce much more water. So So in this case, we can see this process is an energy saving. And but for such membranes, the ceramics, if we made a very large size, is usually some, especially the hollow fiber configuration is usually broken. So we developed the metal support carbon nanotube super hydrophobic membrane. So because the metal, the stainless, is a very flexible structure, and also it has excellent mechanical and electrical properties. And we we just applied such membrane using the anode. And so for DCMD process, the key challenge is for such membrane is the corrosion. But if we implied the membrane as anode, so because the electron can be supplied from the titanium electrode, so this the anti-corrosion can be achieved, and also we can achieve the membrane folding. But if the high porcelain wastewater, there are some special species low energy low surface energy species exist. It's usually there are issue of the wetting issue for membrane distillation process, and our idea using to develop ceramics based nanoporous membrane, the UIO66 morph membrane, to construct such selective layer to achieve the harsh distillation. And so this is the idea of the method of how to fabricate such membrane, and also we use the evaporation to achieve such function. And we found that such membrane can be operated at high temperature and with a very stable long-term stability and mild folding mechanism. After the long-term operation, we can observe that no change, no damage on the membrane surface. And so generally we observed people say the defects play a negative role in the separation performance, especially in selectivity. For morph membrane, because morph is a polycrystalline structure, so we must keep the intercrystalline defects minimized. We must minimize the intercrystalline defects, but nobody concern the intracrystalline defects. So we create the missing linker in intracrystalline defects in the ceramics-based morph membrane UIO66 to improve the water performance while keeping the unchanged the salt selectivity. So, and we applied such membrane by the evaporation, and we found such membrane can be also observed operate at a much longer time. For example, can be operated at a high temperature for as long as 10 days. And we also such membrane. If we have also developed the ultra thin membrane, so around 100 nanometers membrane without the intercrystalline defects. So the membrane, the flux is much higher than current zeolite and the morph membrane. And even the membrane are used in the high concentration chlorine solution, the membrane structure and the performance also keeps very stable. So finally, we understand why the intercrystalline defects can enhance the water permeability properties while keeping the salt rejection unchanged. So we can so by combine the simulation and the experiment result, we can contribute. There are two aspects. One is enhance the absorption ability if intracrystalline defects were created, and the second one is enhance the diffusion ability. So because the intracrystalline defects can slightly enlarge the power window of the membrane for water, for easy transport of water molecule. So I would like to briefly make a conclusion. So low-cost membrane can be fabricated in lab and also large-scale produced. And we also developed ceramics FO membrane and nanofilm membrane for treatment of low surrounded with water, and also the evaporation membrane and MD membrane, like the ceramics-based carbon nanotube network and the MOF membrane can be used for distillation of hypersaline water. So finally, I would like my students and collaborator and also under the projects. So finally, I would like to introduce three special issues in the distillation journal. So first one is the special distillation and cover the 19, and the second one is the membrane distillation. So Nordin and other 4 guest editor, and we are also organizing such special issue. Finally, the special issue, the ceramics membrane for water treatment, organizing water research. We welcome to submit your nice papers. So thank you very much.
Yeah, thank you very much. And in the any questions from the audience, from the chat? I have one question that in your last talk, when you focus on the really insight of the material to highlight the role of the defects in the transport of them the water. In that case, do you think that how that's suitable to upscale that system for the large modules?
So for large modules, we just this study just in the lab scale. So use a small size.
No, I mean just thoughts.
Yeah. So if I think the key problem is to synthesize the larger dimension of such membrane. So yeah.
And a second question, that in that membrane, so the key role is played by the top layer. Do you think that is it possible to use steel polymeric substrate, which might also have quite good mechanical properties? Let's say if you use PEEK, which is quite robust and durable, towards still reduction of the cost of the membrane, because you might probably don't need to use a ceramic support.
Yeah. So because the synthesis of the MOF membrane, especially at high sodium hydroxide solution, so maybe the ceramics substrate is much better.
Okay.
Yeah. Okay. So also there are some other studies focusing in incorporation of MOF crystal into the polymer membrane for preparation. So yeah.
Okay, thank you very much, and have a nice day.
Thank you, Alex.
Thank you. Bye.
Thank you.